So let's take a look at this complex numbers question from the Leaving Cert Ordinary Level 2012, paper 1. It's question 3, and we're told that the complex number z is equal to 1 minus 4i. And they ask us to plot initially z on the Argand diagram, and then minus 2z. So z, first of all, if we take a look at it, z is the number 1 minus 4i. So we're going to go over 1 on the real axis, and then down minus 4 on the imaginary axis. And that's the complex number z plotted on the Argand diagram. Minus 2z, there's going to be a little bit of a calculation first. Minus 2z is minus 2 multiplied by z, which is 1 minus 4i. So place z in a brackets beside the minus 2. We're going to multiply this out, so minus 2 by 1 is minus 2, and minus 2 by minus 4i is plus 8i. So minus 2z can be better represented as minus 2 plus 8i, which is quite easy to place on our Argand diagram. We're going to go back to, so on the real number line we go back to minus 2, and then we're going to go up 8 on the imaginary number line. And that is the complex number minus 2z. The B part of the question then is concerned with the modulus of a complex number, and they ask to show that 2 times the modulus of z is equal to the modulus of minus 2z. So first of all, what's the modulus? Well, the modulus is the distance from the point 0, 0 on our Argand diagram to the complex number z. So we're going to find the modulus of z and then multiply it by 2 for the left-hand side of this equation. For the right-hand side of the equation, we're interested in the distance from the complex number minus 2z back to 0, 0. And when we find the modulus of minus 2z, that will be the right-hand side of our equation. So we have a formula for calculating the modulus of a complex number, and it says that if z is equal to x plus iy, where x is the real part of the complex number, and the yi is the imaginary part of the complex number, then the modulus of that complex number is equal to the square root of the real part squared added to the coefficient of the I part squared. Note that we don't put any i's into this formula. We're only interested in the coefficient, the number beside the I part, the imaginary part. So, finding the complex number first of all of z and multiplying by 2, we're going to have 2 times the modulus of z, which is 2 times the modulus of 1 minus 4i. And then applying the formula to apply the modulus, we have 2 times the root of 1, the real part squared, plus minus 4, the coefficient of the I part squared. That'll give us 2 on the root of 1 plus 16, which is 2 on root 17. Now note, the root 17, that's the distance from 0, 0 to the complex number z. So in calculating the modulus of minus 2z, we're aware that minus 2z has already been simplified to minus 2 plus 8i. To use the modulus formula, we have to have the complex number in the form of a real part plus or minus an imaginary part. If that work hasn't already been done, we need to do that before we apply the formula. So the modulus of minus 2z is equal to the modulus of minus 2 plus 8i, which is equal to the square root of the real part, minus 2 squared, plus the coefficient of the I part, 8 squared. That gives us the root of 4 plus 64, which is the root of 68, and this can be simplified into 2 root 17. Note that our calculator will do this work for us. It'll simplify root 68 into 2 root 17, but if we're wondering where that came from, well, root 68 using the root of surds can be split into the root of 4 times the root of 17, and the root of 4 is 2, which is 2 times root 17. So we know that the distance from minus 2z back to the origin is 2 root 17. And so finally we can see, hence, 2 by the modulus of z is equal to the modulus of minus 2z. Both are equal to 2 root 17. The C part asks us, what does part B tell you about the points you plotted in part A? So in part A we plotted the complex numbers z and minus 2z. And in part B we found out that the distance from z to the origin 0, 0 is root 17, and that the distance from minus 2z to the origin 0, 0 is 2 root 17. So what that tells us is that the distance from the origin to the complex number minus 2z is twice the distance from the origin to the complex number z. 2 root 17 is twice root 17. The D part of the question is again concerned with the modulus of a complex number. It asks us what value would we add to z so that the modulus is then 5. So graphically what they're asking us is, where on the diagram would there be a point such that the distance from that point back to the origin would be 5? Now, the starting point is that we have a formula for the modulus, and we know that z is 1 minus 4i. And so we're being asked, what would we add to 1 minus 4i? So some unknown number k that we would add to 1 minus 4i, such that the modulus of this new complex number would be a distance of 5 from the origin. So looking at the question from a purely algebraic point of view, we'll write down that the modulus of z plus k is equal to 5. We'll sub in 1 minus 4i for the z plus the k, and the modulus of that is equal to 5. We know that when we're using this modulus formula, we can only have a real part and an imaginary part. And within the modulus notation here, we can see we have 3 terms. We're told that k is a real number, and so we're going to add k to 1, the real part of z. And we get that the modulus of 1 plus k minus 4i is equal to 5. Now 1 plus k is the real part, and minus 4i is the imaginary part. And so to apply our formula, we have that the square root of 1 plus k squared, the real part squared, plus the coefficient of the I part squared minus 4 is equal to 5. To get rid of the surd from the left hand side, we're going to square both sides. And so on the left, we have 1 plus k squared plus 16 is equal to 25. There's 2 methods to finish out this question, and we'll look at both of them. So the first method involves removing the 16 from the left hand side by subtracting a 16 from both sides. And we get that 1 plus k squared is equal to 25 minus 16 is 9. We're going to get the square root of both sides to give us 1 plus k is equal to plus or minus 3. And we're going to split the sum into 2 now. So we have 1 plus k equals 3, or 1 plus k equals minus 3. Solving each of these equations by subtracting 1, we get k is equal to 3 minus 1, k equals 2, and k equals minus 3 minus 1, k equals minus 4. And so these are the 2 values for k which satisfy this original equation. Just to check those values, if we have the complex number 1 minus 4i, and if we add 2 to that complex number to get the complex number 3 minus 4i, that this is a complex number whose modulus is 5, and therefore this complex number is 5 from the origin. Similarly with the k equals minus 4, if we take the number z, 1 minus 4i, and we subtract 4 from this complex number to give us the complex number minus 3 minus 4i. So this would also be a complex number whose modulus is 5, whose distance from the origin is a measure of 5. To look at the alternate way we could have solved for k, so we have here that 1 plus k squared plus 16 is equal to 25. 1 plus k squared is 1 plus k times 1 plus k, which is 1 on 1 plus k on 1 plus k, plus the 16 equals 25. We're going to multiply out the brackets to give us 1 plus k plus k squared plus 16, and subtracting 25 from both sides, we get minus 25 equals 0 to make a quadratic. We start with the k squared term, so k squared plus 2k. 1 and 16 is 17, minus 25 is minus 8 equals 0. We factorize the quadratic to give us k plus 4, k minus 2, which will give 2 values of k as k equals minus 4 and k equals 2 as previously found.